We know Apollo 11 landed on the moon. We know about Armstrong and Aldrin. But what about Collins? And after the mission returned, what then? Alone, 45 miles above the moon's surface, Michael Collins completed an orbit every 2 hours. He listened to the progress of the moonwalk and waited for the moment when his companions on the surface would lift off to rendezvous with him. Collins orbited the Earth 30 times, and 30 times he saw the Earth rise over the horizon of the moon. With the flight recorders documenting every second of his wait, Michael Collins, the lesser known of the Apollo 11 crew members, had time to ponder the Earth and the moon as he travelled alone just above the moon's surface. Flying away from the barren surface of the moon, seeming to drift up to its destination, the Eagle headed for the safety of the moon orbiter. Within this strange ship, along with the two astronauts, there were triple-sealed vacuum boxes of soil and rocks collected by Armstrong and Aldrin on their walk across the moon's surface. Locked within these rocks were secrets of the ages to be analysed and studied by a fleet of scientists back on Earth. These pieces of soil might hold the answer to some fascinating age-old questions. The age of the moon and how it was formed, the age of the sun, how life began in the cosmos, and was there ever life on the moon? Was the moon once molten and volcanic, or has it always been cold and dead? Was the moon once part of the Earth, or was it a wandering planet captured by the Earth's gravity eons ago? How hot was the sun 3 billion years ago? Slowly the Eagle returns to Columbia. And when Armstrong, Aldrin and their cargo had been successfully transferred back to Columbia, Columbia fired out of orbit and began its 3-day fall back to Earth, where the recovery fleet was waiting for its splashdown in the Pacific. Magellan was the first satellite to provide detailed images of Venus. The secret of Magellan's success is a sophisticated radar instrument that operates with incredible speed and efficiency. During a burst of activity that lasts less than 1 second, Magellan acquires imaging, altimetry, and radiometry data. This information is used to make images of the Venusian terrain, to determine the heights of surface features, and to measure the microwave energy that is naturally emitted from the planet. Magellan gathers data for approximately 25 minutes during each 3-hour orbit around the slowly turning planet. Starting at the North Pole and moving south, Magellan maps and swathes her strips that cover an area of about 16 miles wide and nearly 7,000 miles long. Twice during each orbit, Magellan turns its dish antenna toward Earth and transmits the data it has just acquired. While this happens, engineers on Earth track the change in motions of the spacecraft to learn about Venus's gravitational field. The large antennas of NASA's Deep Space Network receive the string of data from Magellan, then transfer it to NASA's Jet Propulsion Laboratory. Computers process that data into 15-foot-long image strips. These strips provide the first look at what Magellan has discovered. Additional processing of the strips reveals exciting and sometimes puzzling details. A massive lava flow that appears to come from the rim of an impact crater. A 4,000-mile-long lava channel that is unequaled in the inner solar system, and an unexplained jet-like streak associated with another impact crater. Dr. Steve Saunders, the project scientist, said Magellan had given us a more detailed view of Venus than we've ever had before. Needless to say, scientists and their students are thrilled not only with the quality of the data, but by the quantity. They've begun to use some new evolving computer technology to combine the images with altimetry data and make simulated flights over the surface of Venus. Although Magellan completed its first mapping cycle in May of 1991, its exploration of Venus will continue for several years. In the desert northeast of Las Cruces, New Mexico, NASA's White Sands Test Facility provides the testing on materials and systems for the space program. The goal at White Sands is to minimize flight risks as much as possible. Safety, no matter what, is the first concern. From rocket engines to film for a camera, everything flown on a manned spacecraft has to be tested. Carefully controlled tests are used to determine the strengths and weaknesses in hardware. This testing is crucial to successful space travel. Taking the risk here on Earth first will help avoid having to solve a problem miles away from home in an unforgiving space environment. The moderate weather, arid climate, and remote location make this an ideal site for propulsion and hazardous material testing. Built in 1964, facilities here can test the entire propulsion system at one time to see how the components all interact. The White Sands facility began its propulsion work with the development and testing of Apollo's service module and lunar module engines. These engines were crucial to the success of the Apollo missions. Over the years, White Sands has tested more than 300 engines in over 2.1 million firings. The service module engines put the astronauts into lunar orbit, and then the lunar module descent engine landed them on the moon. The lunar module ascent engine blasted them off the moon and back into lunar orbit. 4 dozen tiny reaction control engines on the lunar module and command service module steered the vehicles through space. And the service module engine brought them home. Each test ensures that all engines used in the space program are safe and reliable. It was the afternoon of May 14, 1973, when the unmanned Skylab Saturn workshop was hurled aloft at Cape Kennedy on the way to its assigned orbit, 236 nautical miles in space. The cloud cover was heavy on launch day and prevented tracking cameras from seeing an event that occurred about 1 minute into the mission. At the point of maximum vibration, telemetry sensed premature deployment of the meteor shield, followed by a weak electrical signal from the workshop's solar arrays. Clearly, there had been a problem. But the exact nature wasn't known until after orbital insertion. During the first revolution, Skylab's temperatures began to rise rapidly, and pieces of the puzzle started to fall into place. NASA engineers surmised that the anomalies were most likely related. It was felt that the meteor shield had been completely lost at deployment, which accounted for the high heat levels. Also, that fragments of the meteor shield had jammed or otherwise hindered full deployment of the solar array panels. Failure of these panels, which were designed to furnish about half of Skylab's electrical power, meant that the total power burden would have to be borne by solar panels on the Apollo telescope mount. By early evening, workshop temperatures had risen above the level of safety. Launching of the crew the following day received an indefinite hold pending satisfactory solutions. Flight support and engineering teams were immediately set in motion to find the answers. At stake was the future of the entire Skylab program. One of the benefits of the space program has been the products and materials that have come about as a result of the challenges of exploring and experimenting in space. Some of those materials are in everyday use now. Although computers themselves did not come from the space program, the heavy demand on computational power by the space race helped push development faster than otherwise would have happened. Even some of the computer games played started out as training simulation software. Simulation rides at amusement parks were also originally from those used to prepare astronauts for their trips. The bounce that was put into the moon boots is now found in some tennis shoes, and the scratch-resistant coating for your sunglasses comes from the space program. Artificial soil was developed for growing plants in space. A thin polyester film used to keep radiation away is now sold as a space blanket. With ongoing experiments in space, there's no telling what will be the future developments. The year is 1962. Lieutenant Colonel John Glenn of the United States Marines in Friendship 7, the America's first historic manned orbital spaceflight. A £250,000 pounds of rocket with thrust equal to 3.5 million horsepower will hurtle a 168-pound astronaut into space. Never in all of history have so many people shared without censorship an adventure of this magnitude. The time draws near, and soon the Earth Pass indicator in the capsule will start showing John Glenn his changing positions above the world. And then the countdown begins in earnest. Glenn reports that everything is in good shape and all systems are go. The capsule is turning around and Glenn reports that he feels fine. For John Glenn, alone in Friendship 7, the long and awesome panorama of the world curving beneath him is revealed for the first time. He reports that he can see the booster just behind him a couple of 100 yards. Glenn is told that he has go for at least 7 orbits. The next transmission is Bermuda, the first station along the way. After passing the station in Connell, Nigeria, Friendship 7 races above Africa at 17,545 miles per hour, 300 miles a minute, and 4 miles for every heartbeat of John Glenn. Above the Indian Ocean flashes Friendship 7 far from human sight, seen only by the electronic sensors of the coastal sentry as she records the lightning passage of the man in space. For John Glenn, the familiar time references of Earth no longer apply. For he journeys around the world in just 88 minutes. Computational fluid dynamics, or CFD, is the name given to science of the flow of real air around proposed aircraft. Computations that describe how an aircraft or missile move through the air. Aircraft used to be designed by the intuitive use of the flow equations, trial and error, and experimentation. Today, understanding of the physics of flight has been enhanced by CFD. The 5 governing equations of fluid dynamics are solved at each point on this grid. There are millions of grid points, and the computer solves the 5 equations at each one. Each of the 5 equations is solved at thousands of times a second in order to arrive at the final converged solution. With this massive number of equations, research scientists reduce the data to provide direct visual presentations of flow around an aircraft. CFD can visualize flow in air or water. It even helped medical engineers design and look at this proposed artificial heart. Computer graphics uses slices of data to look at different 3D surfaces. Here we see a section of the Space Shuttle orbiter engine, used to redesign components in the shuttle. This recreation of flow inside the turbine of a jet engine is a stunning achievement. It required 22 trillion computations. Rocket scientists use the 3-dimensional view of the sonic surface of a proposed body design. The sonic zone is the zone where air passes from subsonic to supersonic speeds. An example of computer power is the aerospace plane. Designed to travel at 18,000 miles per hour, it repeatedly changes the physics of flight and outruns the capabilities of wind tunnels. To know what's happening at speeds of Mach 13 and beyond, supercomputer replication of flight is absolutely essential. After 5 days, 80 orbits and 2.2 million miles in space, Challenger completed its maiden voyage with a perfect landing in the Mojave Desert in California. Challenger was then quickly prepared for its next flight, Shuttle Mission 7. Mission 7 would for the first time utilize a 5-member team of astronauts, including the first American woman to fly in space, Sally Ride of Encino, California. According to Sally, as soon as NASA made the decision to bring women into the program, they treated them just as they did the men. Her training regime was just as physical, and the flight assignments just as varied. Commander Bob Crippen of Beaumont, Texas, had already flown the shuttle once before as the pilot of STS-1. That first mission was a test flight to evaluate and verify the shuttle's systems performance. The Space Transportation System was then able to carry a variety of payloads. According to astronaut Crippen, the shuttle is just a big space truck hired to haul multiple satellites into orbit around the Earth. The only other way of putting up satellites is with expendable booster rockets, which makes the shuttle a more economical and reliable way to get the job done. The spacecraft looked much like its sister orbiter, Columbia. The two were roughly the same size. But Challenger's lighter and stronger construction, together with its more powerful engines, enabled the new orbiter to carry more than 15,000 additional pounds of payload.